Let's continue by talking about the different types of plate tectonic boundaries that occur. And we'll also mention hotspots, which I want to repeat are not plate tectonic boundaries, but they can tell us something about the mechanism behind plate tectonics because they're related to convection in the mantle. And it can also tell us something about how those plates are moving by reading the effect of hotspots over time. There are 3 different types of plate boundaries that reflect different types of motion. There are divergent, meaning moving apart. There are convergent boundaries, meaning moving together. And there are transform boundaries, meaning moving laterally relative to one another. These different types of plate tectonic boundaries have different characteristics. They're going to have different strength and depth of earthquakes. They're going to have different amounts and different types of volcanism. They'll also have different morphologies. Mountains will exist on some and not on others. I also want to mention that depending on whether it's oceanic or continental crust that's diverging or converging together, they're going to behave differently. Because remember, we said that this continental crust can't subduct. It's going to be important. Let's talk about each of these. Here is a oceanic divergent boundary. Some features that we see here are that we have rifting, these rifts forming in the very center of the mid-ocean ridge. But that you'll also have this mid-ocean ridge that forms where it's slightly higher in the center than it is on either side. Where these plates are separating, as a result of decompression melting in the mantle, this otherwise solid mantle material is going to melt and fill in this gap, creating new oceanic crust. And that will happen over time as the plates diverge apart from one another. So divergent boundaries are an area of major volcanism to form that new crust. It's the principal place that new crust is formed. You do also have some earthquakes as parts of these plates grind against each other, like right there, where there are offsets in between the rifts. But for the most part, the earthquakes at these locations are relatively weak compared to the other boundaries. And that's because most of the motion of the plates is apart from one another. Because it's not together, those rocks aren't grinding against each other, creating earthquakes. The one really prominent example of where a continental plate boundary seems to be divergent in nature is the East African Rift Zone. In this area, it seems like the Horn of Africa is starting to separate away from the rest of the African continent, and a new plate boundary is developing. In these areas, you have rift valleys as the land pulls apart. You have volcanoes as those rifts get filled with magma. And you do have earthquakes, somewhat more severe than in the oceans, as these blocks move against each other to reaccommodate the fact that you're forming a rift there. You can see evidence of this rift zone just by looking at a satellite image or a map of the African continent, where a lot of these rifts have been filled in by long, linear lakes, or in some cases, rivers. And it seems like some mountain ranges are being split by this rift forming. Three different types of convergent boundaries we can talk about. We can talk about where ocean meets ocean. So that's oceanic plates, oceanic crust meeting oceanic crust. Either one could subduct in this instance, but in either case, one of the plates is going to start subducting as the plates push together. Because plates are pushing together, anywhere that they're grinding against each other, you can have earthquakes happen. And so you can have earthquakes that end up happening very deep as the plates push against each other. As the plate gets subducted, part of it may start to melt, especially because it's wet and the additional moisture helps melting. That produces extra magma at this area, which produces a volcanic arc. The Mariana Islands are an example of this, where all of these islands are volcanic, but they're right next to what is actually the deepest part of Earth's ocean, the Marianas Trench. That's where, that's the actual trench where the plates are subducting the deepest, and you still have expression of the surface ocean there. So that's what we call an oceanic trench. Here's a picture of what one of those islands can look like. They tend to be relatively isolated, somewhat linear ranges. Definitely volcanic in nature. You wouldn't want to be on this thing when it erupts. But then underneath our boat here from where we're taking the picture, it might be thousands of feet deep already. It might even be miles deep. Those trenches can get as deep as 10 miles deep. The second type of convergent boundary is where oceanic crust meets continental crust. This is occurring now off the coast of South America, the western coast, where the Nazca Plate in the eastern Pacific Ocean is subducting underneath South America. This part looks very similar. You have deep earthquakes here, you have melting, and you have a set of volcanoes form. But these aren't an island. These are going to form on the edge of the continent. In this case, the Andes Mountains are the reflection of that extra magma being added as this oceanic plate subducts and melts. Because this motion is convergent here, not only do you get volcanism, but you get a lot of this squishing motion here, which is going to help build up these mountains by squishing this crust together and forcing some of it to move up to compensate. So these folded mountains generate as well at an ocean-continent boundary in a way that they don't happen at an ocean-ocean boundary. Here we're viewing in the southern direction, so that's west. And so this is South America. This is the Pacific Ocean. You can see that long chain of mountains. There are lots of volcanoes mixed in here. You also get a whole lot of earthquakes happening in this region. And in fact, this is the area on Earth that has the largest recorded earthquake. I think it was something like a 9.5 in Chile as a result of that subducting motion. So somewhere about here probably is the trench. So the Nazca Plate is subducting underneath the South American plate there. Last type of convergent boundary is when continent collides with continent. As we said, we can't have subduction. Neither of them is dense enough. So instead, we just crush these rocks together a whole heck of a lot, and we generate extremely tall folded mountains. We also generate a lot of earthquakes as these plates try to grind against each other. So we have subduction labeled here, but it's really, look at how little is actually going on. Very little subduction can actually occur, and most of the motion ends up squishing these rocks together, generating very tall mountain belts. The Himalaya are currently the tallest mountains on Earth. The ancestral Appalachian Mountains were one of these continental boundaries, and so those mountains probably were as tall as the Himalaya are today, at least at their heyday about 200 million years ago. The major example of this today is, as we said, it's the boundary of India here. China's here. Nepal is in between. And we saw that image in the very first lecture of the huge earthquake that happened in Nepal in 2015. That's because of the convergent motion of these plates together. Not really a lot of volcanism associated with this because there's so little subduction, but it's mostly very strong earthquakes and very tall mountains. Last types are transform fault boundaries. At a mid-ocean ridge where these plates are moving apart, because plates aren't flat, they're curved, like we can see here with Earth's surface. There ends up being this weird feature of geometry where the mid-ocean ridge itself ends up being offset in certain spots. Here, the plates are moving apart. Here, the plates are moving apart. But in between to connect these ridges is an area where the plates are sliding past each other. That's called a transform fault. In this area, the plates aren't separating, so this is an area where we don't get volcanism. But we do get earthquakes as these plates slide past each other and rub against each other. You can't really see a surface expression of these because these are all underwater. So if we went and took a picture of one, it would just look like open ocean. But they can be sources of earthquakes that cause disasters on land. Continental transform faults can also happen where any plates are sliding against each other. Like the edge of the Pacific plate is actually just a little bit of continental crust, and North American plate is sliding in the other direction. And this is occurring on America's west coast, the San Andreas Fault, which puts at seismic risk basically everything on America's west coast, but especially LA and even more so San Francisco are at high risk because of this fault. We can even see that this fault has been moving over time because this stream here has at times connected to this. It's just that the plates have been sliding next to each other for so long that these have separated over time. This was the oldest, and this is the current connection between this stream and this stream here. If we look at the distribution of these plate boundaries, we can see that where these plate boundaries meet up with one another, they outline the outside of these tectonic plates. And so we have a whole lot of convergent plate margins along the western rim of the Pacific Ocean. So there's a lot of earthquakes and a lot of volcanoes in this area. There's a lot of transform faults over here. So we have a lot of earthquakes there as well, and then a few dotted volcanoes. Lots of convergence along that South American plate border. And in contrast, North America is a lot more quiescent. There's really just a lot of divergent plate motion along the center, separating North America and Eurasia as these move apart. So we get some volcanism, which contributes to Iceland, and some undersea volcanism. But for the most part, there's not a lot of seismic danger, at least from the plate boundaries in the center of the Atlantic Ocean. Because the total amount of crust must stay approximately the same, and we don't have any evidence that Earth is expanded or contracted over time, these two types of boundaries are going to be balanced. Divergent boundaries are where we create crust, because that mantle partially melts and creates new continental crust there. And then the convergent boundaries, where oceanic plate subduct, is going to destroy crust. So we probably have about the same amount of divergent and convergent plate boundaries on Earth's surface. After we talked about this, you should be able to come up with an example of one of each of these, at least where we could see each of these types today. And if you're not sure, you could go back and look at that map that we showed. Where would you see an example of continental-continental convergence, right? The big answer that we gave was the Himalaya. What about continent-ocean convergent? We talked about the Andes. There are certainly many more. Ocean-ocean convergent. There are a few places in the Pacific Ocean that match up with that. Continental divergent, the major one was the African Rift, the East African Rift, I should say. Oceanic divergent, how about the center of the Atlantic Ocean? Continental transform boundary, the main one was San Andreas, that we hear about a lot in the US because it's the most applicable. And then ocean transform boundaries are in a host of different places, but they just offset some of these divergent plate boundaries. What are hotspots? Hotspots are isolated points where it seems like extra hot mantle material is rising toward Earth's surface. These upwellings of deep mantle plumes can create volcanoes in the middle of plates instead of at their boundaries. And that's actually what has created the Hawaiian volcanoes. over time, as plates move over the hotspots, which remain relatively stable, so we can see the motion of the plate here. Over time, the plate moves and volcanoes grow in a line, and they grow from oldest to youngest. So at one point, Kauai was actually sitting over this hotspot, but it has moved. A little bit later than Oahu was, and a little bit later Maui was. And these volcanoes have mostly gone dormant because the hotspot is sitting directly under the big island of Hawaii right now, feeding Mauna Loa, Mauna Kea, Kilauea on that island. And because it creates this line of volcanoes, if we figure out the age of each of these volcanoes, then we can use that information to figure out how fast the tectonic plates have been moving over the hotspot over time. And we've done just that with these age dates of the volcano that we see written here. This being the most recent in Hawaii, and this being a series of volcanoes that are really only seamounts at this point, that don't even pop above the surface of the ocean because they have eroded away. We can see evidence of one right now in the US in Yellowstone. A hotspot feeding the Yellowstone caldera is what creates all those magnificent hot spring features and geysers and fumaroles that you can see around the Yellowstone area. But it also means that if we get a whole extra surge of magma hitting the Yellowstone area, that we could have a supervolcano erupt.